I said we would wait until 3:05, but we have a pretty good quorum. We have about 20 people, so I think let's get going. It is my pleasure to introduce Dr. Shruti Puri. She received her PhD from Stanford, and then after that, she did postdoctoral research work at the University of Sherbrooke and Yale University. And since 2020, she joined the faculty at Yale University Applied Physics Department. Her research is around different aspects of quantum information processing, quantum optics, quantum control of open systems, quantum error corrections, and quantum algorithms. And today she's going to talk to us about noise-tailored quantum error correction for next generation qubit technologies. And she said she welcomes questions and comments in between, so feel free to interrupt if you have doubts or anything to add. Okay, floor is yours, Shruti, take it away.
Thank you, David, for that introduction. Let me share my screen 1 second. All right. You can see my slides?
Yes.
And my cursor?
Yes.
Awesome. Okay. Yeah, thank you for the invitation. I'm just going to start my timer so that I know where I'm at. And please don't hesitate to ask questions in between. So I would like to start by first acknowledging my collaborators, colleagues, especially the postdocs and students whose ideas and hard work is behind, some of the ideas that I'll be showing today. All right, so the main motivation for my talk is that we all want to build a universal fault-tolerant quantum computing architecture. For that, we would like to increase the thresholds for fault tolerance so that we can work with noisier quantum hardware, which we may have in the lab today or we may have in the lab in the next few years. We would also like to decrease the physical gate and qubit overheads associated with implementing fault-tolerant protocols. So the main message that I would like to convey today is that when you're thinking about scaling your system for error correction, think deeply about the noise affecting your qubits, because not all errors are created equal. Some errors are very contagious and they rapidly spread through the circuit, whereas there are other errors that are easier to detect and correct. So what we would like to do is build smart qubit hardware where such that the architecture is tailored to suppress bad errors, that is, the errors that are hard to correct, even if it means that we have to slightly increase the rate of good errors that are nonetheless easier to detect and correct. So I will show you the rest of in the rest of the talk. I'll give you many examples of such good and bad errors and how we can use these good errors to improve the performance.
When you say good and bad errors, are you thinking only of errors within the qubit subspace, or are you also considering things like leakage that can be quite nasty?
Yes, so I'm going to talk about that in this slide.
Okay.
Awesome question. And that brings me to the next slide. So let's think about what errors are happening in the system. So the first common error is error happening in the computational subspace of your qubit. And these errors can be treated as poly errors. So your environment is measuring qubit along the poly X, Y, or Z axis. This is the example of a single qubit poly error channel. So PXP by PZ is the rate at which the environment is measuring the qubits along the X, Y, and Z axis. Typically, we think about depolarizing noise such that the probability of X, Y, and Z errors are all the same. But in many cases, the qubit can be biased. That means it couples to the environment along only one axis of the block sphere. And these are called as biased noise qubit. So suppose the qubit is predominantly coupled to the environment along its Z-axis. So the environment is more likely to measure your qubit along the Z-axis than the X and Y axis. That means the probability of X and Y errors are going to be suppressed compared to probability of Z errors. So in this case, we not only have to define the total error rate in the system, which is probability of X plus Y plus Z errors, but also we have to define the bias, which is the ratio of the dominant error, which is the Z error, to the non-dominant error, which is the X and Y errors. Another type of error can be erasure. So suppose your qubit leaves your computational subspace, but you're able to actually detect that this transition has happened with high accuracy. Then what you can do is, as soon as you see that the qubit has left the subspace, you will, kind of throw away that qubit and put a fresh qubit in its place. And this is known as erasure error. So you don't know, when you replace with a fresh qubit, you don't know whether the original qubit suffered from X, Y, or Z errors. You just know that there was an error in that location. You just don't know the type of error there was. So such unknown errors at known locations are called as erasure errors. It is known that quantum error corrections with high code capacity thresholds of about 50%, is known for infinitely biased noise and erasure errors. By code capacity threshold, I mean threshold assuming that the circuit you use for error correction is perfect. So in that case, we know that we get really good codes when you have biased noise or erasure errors. In this talk, I will focus more on what happens when there's errors in the error correction circuit itself. And of course, this is what really happens in the lab. So I'll tell you how to think about errors happening in the circuit and how you can still achieve high thresholds to bias noise and erasure errors against real circuit level noise. In the first part of the talk, I'll mostly focus on circuit-based quantum computing. And in the second part of the talk, I'll talk about the measurement-based model of quantum computing. Okay, so recently a surface code called the XZZX surface code has been introduced. This surface code involves qubits arranged on 2D lattice. You have one type of stabilizer, which is the 4-body XZZX operators acting on the 4 qubits around each of the plaquettes. Of course, at the boundary, you have the 3-body operators. Now, if there's a Z error on one of the qubits, then it'll create defects along the horizontal axis in the surface code, along the horizontal direction in the surface code. And if you have X errors on your qubits, then it'll create defects along the vertical direction. So if you just have Z errors, so if you have infinitely biased noise and you just have Z errors, you can only have defects along the horizontal direction. And it turns out that this code then reduces to a repetition code, and therefore it has high thresholds to the error. So this plot on the bottom left is from this paper. And if you look at the blue dots are the thresholds against Z bias noise. So on the x-axis, you have the bias, and the y-axis is the threshold. So the threshold increases from about 10% to about 50% when the bias increases from half, which is depolarizing noise, to infinite bias, which is pure Z noise. But even at moderate biases, you get like biases of about 100 to 1,000, you get thresholds between 30 to 40%. But now let's think about, so now let's think about what happens when you have errors during, in the error correction circuit as itself. So how are you going to measure these stabilizers? You're going to put an ancilla qubit at the center of each of the plaquette. You will initialize it in the plus state and measure it in the X spaces. And in the middle, you will do a bunch of control NOT and control Z gates between the data qubits and the ancilla qubit. So if you just have pure Z noise, you can show that if you have Z bias noise, then you can show that the errors during the preparation, measurements, and the control Z gates are going to be Z biased as well. The problem happens when you try to do a control NOT gate. If you naively try to do a control NOT gate on 2 qubits, then it turns out that a physical Z error in the target qubit during the control NOT gate propagates as Y errors. So in fact, 25% of Z errors in the target qubit gets converted to Y errors in the qubit itself. And so because of this, the noise channel of a CNOT gate is not biased. That means you will not get this improvement to thresholds in the circuit level case as you would have expected otherwise. In fact, there's a no-go theorem which says that native bias preserving CNOT gates are strictly impossible in are impossible in strictly 2-level systems. So now I want to show you what is the impact of having a bias preserving CNOT gate versus not having a bias preserving CNOT gate. So suppose God magically gives you a C0 gate, which has bias noise. So there's only Z errors in the C0 gate. And you now build the XZZX code using this kind of C0 gate. So on the x-axis, I'm showing the probability of Z error. So this probability of Z error on a single qubit, during any gate operation or measurements or idle, etc. On the y-axis is the logical failure rate for the XZZX code, and I plot the logical failure rate for different sizes of the code itself. And all these lines intersect at a point, which gives you the threshold. So in terms of the Z errors in a single qubit, the threshold is about 1%. In terms of a 2-qubit gate infidelity, the threshold is like...
Is your logical error rate sensitive to your decoding procedure?
Yeah, so this is minimum weight, standard minimum weight perfect matching.
Okay.
So the threshold in terms of the 2-qubit gate error is 2%, which is just 2 times the x-axis. It's because 2 qubits are participating in the gate. Now, if you had actually used the C0 gate, with a standard C0 gate in which 25% of Z errors are converted to Y errors, then the threshold decreases to about 1.7%. But now, the difference between 1.7% to 2.1% is not really that much. And so this might not excite you. However, having a small change in the threshold can make a big impact on the logical error rate. So if you look at the same size of the code implemented with bias preserving C0 gate versus not having a bias preserving C0 gate. So let's look at the 8x24 lattice in both cases. So these purple dots. So for the same x-axis, which is also like the same total physical error rate, you see that if I had the noise to be Z biased in the C0 gate, then my logical error rate is about an order of magnitude smaller than if the errors in the C0 gate were not biased. So this really tells you that it's not just the total error rate in your gate that matters, the structure of the noise in your gate also matters. And when you make your experiments, think about not just the total infidelity, think about what is infidelity coming from. So fortunately, we have shown that if you are able to make a superconducting Kirkat qubit, superconducting Kirkat qubit is a bias noise qubit. This is a continuous variable qubit, so you can use that property to go around the no-go theorem. And in this qubit, you can actually do a bias preserving C0 gate. And so in this paper at the bottom over here, we also calculate the threshold for the XZZX code, assuming we have these superconducting Kirkat qubits and we get high thresholds about 6%. To give you, the superconducting Kirkat qubits have been implemented. They're first realized in Michel Zavare's group. In the most recent experiments, and the results are in preparation, in the most recent experiments, the bias that they observed in the qubit was about 500. So this is just a single qubit bias. This is not 2-qubit gate bias yet. They are, the work for 2-qubit gates is underway. So as they're thinking about making the C0 gate, we also need a way to characterize the gate itself. Again, we want to not just characterize the total fidelity of the gate, but we also want to characterize the bias in the gate itself. So we would think about, you would say, okay, let's do some benchmarking experiment on the C0 gate. However, for naive benchmarking, you would typically use, your poly gates like XYZ gates to twirl your noise channel, or you would use a Clifford gate to twirl your noise channel. But you cannot use a Clifford group to twirl the noise channel because Clifford group will contain a Hadamard gate, and a Hadamard gate cannot be implemented in a bias preserving manner, no matter what your, even if you have a continuous variable qubit. Moreover, if you want to twirl with the the poly X and Y gates, the problem is that the X and Y gates are slow. They're as bad, as erroneous as the C0 gate itself. If you try to do it in a bias preserving way, if you don't try to do it in a bias preserving way, then you're gonna like completely unbias your channel anyways. So the main challenge we overcome in this paper is how to correctly benchmark the total gate error and the bias in the C0 gate by just using diagonal Z gates for twirling. All right. So far, I've just talked about thresholds, but it's also important to know how to decrease overheads for logical gate operations. So one of the most challenging tasks in implementing a surface code is magic state injection and distillation. So magic state are resource states that are shown over here. You require them to do fault-tolerant T-gates in the surface code. The problem is that when you first prepare a raw magic state in the surface code, then the logical error rate of the raw magic state scales as the physical gate error in the system, irrespective of the code size of the surface code itself. So now, no matter what is the distance of the surface code, once you prepare a raw magic state on it, you cannot, the fidelity of the raw magic state is not going to be better than the fidelity of your 2-qubit gate, for example, the C0 gate or this C-phase gate in your circuit. That's just it. So of course, now this error rate might not be small enough for you to implement your quantum algorithm. So what we do is magic state distillation. So we take many copies of such faulty magic states and pass it through a distillation circuit, and we get one magic state out with a better fidelity. So the error reduction is by a constant value. So if the error rate in the input magic state scale as P physical, the error in the output magic state can scale as P physical cubed. And of course, you can just concatenate this distillation scheme further and further to get lower and lower logical error rate. But you can clearly tell that this distillation will cause a fast increase in the resource overhead that you require. So what I'm going to show you next is that we can reduce the cost for magic state distillation by improving the fidelity of the raw input magic state by using the operations that are available in the bias noise architecture. Okay. So the idea is to use a 2-qubit continuous ZZ rotation, which is available in the bias noise architecture. You can do it with a high fidelity, and these are trivially biased gates. So in particular, for the magic state that I showed in the previous slide, we will use this gate. So it's a e to the I pi over 8 ZZ gate. We will use this 2-qubit gate to first prepare non-transversally prepare a repetition code, a magic state in a 2-qubit repetition code. This repetition code will correct for Z errors. And then we will grow this repetition code into a larger XZZX surface code by using traditional lattice surgery techniques. So with this technique, with this protocol, we are able to prepare the raw magic state with a logical error rate which scales quadratically with the physical error rate in your gates. So we're doing quadratically better because we had bias noise. And we were able to do this gate with a high fidelity. So to give you an intuition for how much this will affect my magic state distillation, let's look at some modest gate parameters. So let's look at a C0 gate infidelity of about 0.7%, which we expect to be able to reach in the lab in the next year or so. And let's look at the bias of about 2000. So this is still a factor of 4 away from where we have what bias we have in the lab right now, but it's only a factor of 4, and we believe we can reach this number. So now if I had used the magic states prepared using our protocol and passed it through a 15-to-1 distillation circuit, then the one magic state that comes out has the error rate of 10 to the minus 8. But if I had used the standard protocol, then the output magic state fidelity or infidelity will be 10 to the minus 6. So with our protocol, we are able to reduce the logical error rate of the output magic state by 2 orders of magnitude. And in fact, an error rate of about 10 to the minus 8 is enough for you to implement quantum simulation, quantum algorithms for quantum simulations with a quantum advantage.
Are the resources you're using in both cases comparable?
Yes. Yes. Yeah. Okay, so with the error rate of 10 to the power minus 6 is not sufficient to reach, it's not sufficient to give you quantum advantage, but error rate of 10 to the minus 8 is. Okay, so the next error type that I want to talk about is erasures, and this was the work done with Jeff Thompson's group in Princeton, and he was really the person driving this project. So this is in atomic qubits. In particular, we are using the ytterbium atom, neutral atom, and we use the hyperfine states to encode our qubit. So in order to do 2-qubit gates here, we have to excite the, so the hyperfine states are really long-lived and they don't interact much with the other atoms. So to do a 2-qubit gate, you have to actually excite your one state to a Rydberg state. And when the atoms go in the Rydberg state, that's when they can actually interact and do your control Z gates or whatever else have you. Now, the main source of decoherence in this system is a Rydberg state decaying to states outside the computational subspace. So the rate at which Rydberg states decay into the computational subspace is much smaller than the rate at which it decays to these other states. And if this Rydberg state decays to the other states, we can actually do a fluorescence measurement to determine if this leakage actually happened or not. So basically, we have erasure errors. As soon as we see that, indeed we see a population in this 1s0 state, we know that something bad happened to my atom. I'm going to throw it away and bring a fresh atom in. So in this case, we find that, if 98% of the errors were erasure errors, then the threshold comes out to be about 4.15%. So this is really a big improvement in the threshold by just converting your errors to erasure errors. The other improvement that comes in is the distance of the code itself. It turns out that if your code can correct for T poly errors, it can correct for 2T erasure errors. So basically, you get more bang for your buck for the same size of lattice. So here on the x-axis, we are showing the fraction of errors that are, we are showing the fraction of errors that are erasure errors, and the simulation is run on a 5x5. This is that I messed up the plot. Sorry, this figure is showing threshold versus the detected error fraction, and this really shows that the threshold increases from about 1% to 4 to 5%. When you have all the errors are erasures, it's about 5%, and when you have 98% of erasures, you have a threshold of 4.15%. I think there's some mistake in the animation here, because there should be another plot which is not popping up, which should show that when you have erasure errors, the distance of the code is also bigger. So for the same number of qubits, you're actually able to correct more erasure errors. I'm sorry, I don't know, something wrong with the animation there. Okay. So far, we have been thinking about circuit-based error correction, but you can also think about doing measurement-based quantum computing or measurement-based error correction. So first, let me quickly tell you what's the difference between the two. I'm sure many people already know about this, but maybe a few people are not familiar with this. So for them, this will be a quick intro. So when we think about circuit-based computing, we have some qubits that, imagine some solid state qubits, and they're just sitting in some location, and there's in some input state. And we apply gates to these qubits in time and obtain a unitary transformation on that state. Now, instead, you can achieve the same unitary transform in a measurement model. What does that mean? It means that, okay, so these are my 2 qubits with in some input state. Now what I'm going to do is I'm going to add some additional qubits. All of these additional qubits are going to be initialized in the plus state. Then I'm going to do some local entangling gate between these nearest neighbor qubits. So whenever you see an edge between the 2 dots, that means you're doing a local 2-qubit gate. And in particular, in this case, the gate is a control Z entangling gate. Now, after doing these control Z gates, you have created a big entangled state, which is called the cluster state. Now you'll measure all but the last 2 qubits in some basis, in some local basis. So X, you'll do some X measurements, some Y measurements, etc. And what happens if you choose your measurements correctly, then these 2 qubits at the end, the state of these 2 qubits at the end would be the desired unitary applied to the input state. So you have achieved the same unitary transform, but just in a very different manner by doing measurements rather than, applying gates in time. The nice thing so if so in fact a 2D cluster state plus preparations along the plus direction, measurements along the z-axis, and measurements in the xy plane are sufficient for universal quantum computation. And 3D cluster states are sufficient for universal fault-tolerant quantum computation. So you may ask me, why do I care about measurement-based computing at all? Well, in some hardware architectures, it's actually better to do measurement-based computing rather than circuit-based computing. So for especially like for photonic flying photonic qubits, people usually consider the measurement-based architectures because you want to measure your photons as soon as they're prepared before they're lost to the environment. Moreover, the measurements on the photons are actually destructive. You cannot do QND measurements on those photons, right? Because your detectors are basically just eating away your photons. So in that case, again, it's more useful to do measurement-based quantum computing because all these measurements can be destructive. You don't ever want to reuse those qubits again. And in fact, we are now considering measurement-based quantum computing for some superconducting bosonic qubit architectures as well for some special reasons, which I won't go into further details over here. Okay, so let's first understand how measurement-based quantum computing actually works. So the basic idea about measurement-based quantum computing is based on teleportation. So let's look at how I would imagine doing an identity operation in measurement-based computing. So suppose you have some input state. Now you just want to do identity operation on it. So that's like saying I'm going to add 2 other qubits in the plus state. I'm going to do my control Z gates, and I'm going to measure the first 2 qubits in the X basis. So it turns out that you can easily show that the state of this last qubit is the input state up to some poly corrections. Now, this is like a short teleportation circuit because I'm teleporting over 2 qubits, but I may want to build a long teleportation circuit, which is like doing identity for a longer time on in the circuit-based picture. So in this case, I just add more qubits, and the same thing, I do control Z gates, and I just measure each qubit in the X basis. Again, the state of the output qubit is the input qubit up to some poly corrections. Okay. Now, with the same kind of teleportation idea, you can now do gates in the measurement-based picture. So for example, how do you do a Hadamard gate? Suppose this is an input state, and you want to do a Hadamard gate on this input state. Again, you'll add 4 other qubits to the system, do your control Z gates. You'll measure the first qubit in the X basis, the next 3 qubits in the Y basis. And that's like you doing a Hadamard gate on the input state up to some poly corrections. Again, you might want to do an S gate in measurement-based quantum computing. So in this case, you just change your measurement pattern. You now measure first 2 qubits in the X basis, second qubit in the Y basis, fourth qubit in the X basis, and this would do an S gate on your input state. Similarly, you can do a T gate on your input state, which would require you to measure in the T basis, single qubit in the T basis. That is, you want to distinguish these 2 states on the right over here. And now if you want to do a 2 qubit control NOT gate, then you take 2 of these linear chains, 2 of these teleportation chains, and then you just add this extra center qubit here. And then you just measure, the red squares are the qubits that are measured in X basis, and the blue ones are in the Y basis. And then you can easily show that this is equivalent to doing so the output state of these 2 qubits is the input state followed by a CNOT gate. In fact, like I said, the gates, these gate pictures that I've drawn here, gates in measurement-based quantum computing are basically equivalent to teleportation-based gates in circuit model. It's basically teleportation-based gates. That's the main idea. Okay.
I have a quick question.
Yeah.
It's okay. In systems where you say measurement-based quantum computing is better, what are typical spam error rates, and how do those compare to, equivalent gate-based error rates?
They're kind of similar. So, I mean, if you just look at, can I come to the error rates in just a second, because I'm going to talk about thresholds and so on in just a few slides. Yeah, so I'll get to your question for sure. Okay, so now let's look at fault-tolerant error correction, right? So we looked at the previous slides, which told you how to do gates, but now, as somebody said, what about errors? So it turns out any stabilizer code can be converted to a fault-tolerant cluster state using a process called as foliation. So let's look at how one might foliate a repetition code for Z errors. So basically, you have these three states. You have these effectively 3 qubit states that you're teleporting down the chain. And as you're teleporting these states down the chain, you want to measure the stabilizers for your repetition code. So if the repetition code for Z, so if you're implementing the repetition code for Z errors, then this you need to measure the XX correlations between these 2 chains. So what you do is you add, again, extra qubits at the center like so. And now you measure all the qubits in the X spaces. So it turns out that the measurement outcome of these center qubits here is equivalent to measuring the XX correlations between these 2 chains and these 2 chains. Okay. And again, you can think about this as repetition code being teleported in time. So this first patch is a repetition code at time t1, then it's teleported to repetition code at time t2, t3, and so on and so forth. So again, this is again like a teleportation-based error correction picture. Now, the way you actually do error correction is you can observe that, well, you can show that if you multiply the products of the X measurement outcomes on these 4 qubits, or basic qubits around each plaquette, then that product is the product of X measurement should be equal to +1 if there are no errors. If there are errors, then some of them, then they can be -1, and then you just basically decode like a regular repetition code. Interesting thing is that not all of these.
That kind of has the flavor of a lattice gauge theory in a plaquette or something like that.
I guess, yeah.
I just found it interesting. Sorry.
Yeah, no, I'm yeah, maybe yes. So it turns out that this is okay. So before that, so not all layers in this repetition code, for example, need to be present at all the time. Like you just need at a given time, you just need a 2D slice of this whole like 3D picture. So basically, even if you just have this one block, then you can just basically teleport your information back and forth within the block, like move it from here to here, here to back here, here to here, here to back here. And so you're basically creating this a 3D cluster state, but the third dimension is time, basically. It turns out that if you take the regular surface code and foliate it, you get what is called as the Rossendorf-Harrington-Goel cluster state, or the famous RG cluster state. And so the threshold for the regular surface code is the same. Like if you were to do surface code in a circuit-based model versus if you were to do in a cluster state model, then the thresholds are actually the same. Of course, the details are in the devil. There might be some, like if you were to actually implement a surface code, you would actually need a C0 gate or a C-phase gates. But if your system actually cannot do a C0 gate or C-phase gate, or if the gates, C0 gates and C-phase gates are really bad, then effectively the threshold for the surface code will drop. But if you were able to, but you might still be able to get high threshold for the cluster state. So in principle, their thresholds are the same. Again, it may happen for some reason in your architecture, it's easier for you to make the cluster state with operations that are really high fidelity, in which case the cluster state will effectively have a higher threshold. So does that answer the question that was asked?
I'm just curious, like on like actual values.
I'll show that in a second. Yeah. It's the same 1%, 2%, threshold. It's the same thing. But I'll show you more values in just a few slides. So the question that we asked was we have these new stabilizer codes coming up, which have really high thresholds to bias noise. So now can we foliate, say, the XZZX code, which is high thresholds to bias noise, to get a cluster state that also has a high threshold to bias noise? When I first asked this question, I thought the answer is going to be a simple yes. But it turned out that was not the case. And this was a work done by Jehan, my postdoc student, who showed why the regular foliation procedure cannot be used to create the XZZX cluster state with high threshold to bias noise. And then he also, in this paper, showed what is the new foliation procedure you should use to actually get high thresholds for bias noise. So firstly, let me show why the regular foliation procedure doesn't cannot give you high thresholds. So let's look at our teleportation chain. Like that was really our building block. So if you remember, we put this input state, we measure the qubits in the X spaces, we get a qubit out, which is the input qubit in the input state up to some poly corrections. Now, suppose there's a physical Z error in your system. That means a physical Z error will cause the X measurement error to be incorrect. That means it will, suppose there's a Z error on this 6th qubit. So that means X6 is going to be incorrect. If X6 is incorrect, that means you'll effectively be applying a wrong X poly correction to your input state. So now you have actually converted a physical Z error to a logical X error. And so this foliation procedure itself doesn't preserve the bias. And therefore, the regular foliation procedure, even if you use a regular foliation procedure to foliate the XZZX code, you will not get a high threshold cluster state. So what is the solution? The solution is quite simple, actually. You're just going to use a little bit more decorated graph. Now you'll need 2 types of qubits. You'll need some qubits that are prepared in the plus state. You'll need some qubits that are prepared in the 0 state. Whenever there's an edge between the 2 qubits that are prepared in the plus state, that means I'm going to do a control Z gate. If I'm putting an edge between a X type and a Z type qubit, then I'll be doing a control NOT gate. Importantly, the control will always be on the X type qubit, and the target of the control NOT will always be the Z type qubit. And then I'm again going to perform local measurements. The Z type qubits will always be measured in the Z basis, and the X type qubit will always be measured in the X basis. Okay, so I now start with a qubit here, and it's prepared in some input state. And now I'm going to add more qubits, but this time alternatively prepared in the plus state, 0 state, plus state, 0 state. And now I'm going to do all these control NOT gates. Now, the way these control NOT gates are done is in a commuting manner. This control NOT commutes with this control NOT because the control is the same. The target is on different qubit, control is on the same qubit. So all of these control NOTs actually commute with each other, and in principle, you can just do them in one step. Okay, so now I'm going to do these measurements. I'm going to measure the Z type qubit in Z basis, X type qubit in the X basis. And so I can show that the state of the output qubit is the same as the input qubit up to some poly correction. Now, remember, if I have a Z error will not affect the measurement, a Z measurement. A Z error doesn't affect a measurement in the Z basis. So it'll never corrupt the Z1, Z3, Z5 measurement outcomes. A Z error will only corrupt a X2, X4, X6 measurement outcome. And you see a incorrect X2, X4, or X6 will only apply a Z correction to your state. So in this case, a physical Z error can only apply a logical Z error to your output state. And so in this foliation procedure, a physical Z error does not convert to an X error. So this is like a bias preserving foliation procedure. So this foliation preserves the noise bias. So now if I have qubits with purely Z noise, so now I truly want to just implement a repetition code for Z errors, then I just take 3 chains like this. As I'm teleporting the qubits down, I want to measure the stabilizers of the repetition codes. I'm going to put these qubits, additional qubits at the center. Again, measure the Z-type qubits in the Z basis, the X-type qubit in the X basis. And here it turns out that, again, these measurement outcomes of the center black dot qubits, Z-type qubits, measures the XX correlations between the two, the chains. And so now we are ready to foliate the XZZX surface code. So on the bottom left, I'm showing just, just the lattice for the XZZX code, the way we draw it. So you have these, let's just look at these plaquettes. So these are four, you can think about these in the circuit-based model, you'll think about this as four data qubits that are sitting around the plaquette. In the cluster state model, each of this qubit will be replaced by now chains of qubit. And now if I want to measure this XZZX stabilizer, I'm just going to add these ancilla qubits at the center, and that's it. So the measurement outcome of this ancilla qubit at the center actually measures the XZZX correlation stabilizer of the code. And now I might want to create this other plaquette. And so just just to give you visualization, to see how this other plaquette might look like, you just add basically more ancilla qubits and then more connected to other linear chains and so on. So basically, this is how you create the entire XZZX, bias-preserving XZZX cluster state. In this case, for each of the unit cell, the product of the X measurement outcomes of the X stabilizer, the product of the X measurement outcomes on this X-type qubits and the Z measurement outcomes on the Z-type qubit should be 1. A Z error will only ever cause defects in the plane, and an X error will cause defects outside the plane. So if you just have pure Z errors, then the defects will always arise in the plane. And then it's like a repetition code, and therefore it'll have a high threshold. Only the X errors take you out of the plane, cause defects out of the plane. The Z errors keep the defects in the plane. High threshold error correction isn't possible. So now the result is the threshold on the y-axis versus bias on the x-axis. Again, this is circuit level simulation. So I'm actually putting errors, 2-qubit errors on the control Z gate, control X gates and everything, preparation errors, measurement errors, and so on. And as expected, as the bias increases, the threshold for the XZZX cluster state increases, and it goes up to 2%, 2.5% or something for a bias of 10 to the 4. This is the same threshold I would have got if I had actually done circuit-based error correction. There's no difference. Absolutely, there's no difference. Right, and so we compare that with the RHG, the threshold for the RHG, the standard cluster state, which is the RHG cluster state, and here the threshold doesn't improve as a function of the bias. It turns out that the RHG cluster state actually does slightly better if the bias is actually X bias. And in that case, you see a slight improvement, but nowhere near the improvement you get if you had actually used the XZZX cluster state. So did this give you the numbers that you were looking for?
Yeah, I mean, I was just curious, just generally speaking, I was just curious how measurement-based quantum computing is limited in a similar fashion as gate-based, and like if error rates are approximately the same. That's kind of just what I was interested in.
I think Akhil was looking at, he wanted experimental error rates, right, Akhil? Or not? Yeah,
because I look at our systems and like I don't think we could perform measurement-based quantum computing if we wanted, just because our spam is too high oftentimes. So and so I was just curious what you said, other platforms.
Oh, but by the way, if you put high spam in measurement-based quantum computing, the same high spam is going to happen in the circuit-based quantum computing, and it's going to affect the thresholds the same way. So you can't, if you have high spam, it's going to affect both cases. It's not that it'll do worse for measurement-based, not for circuit-based. No, that's a wrong perception.
Sure, okay. But I was just curious, you were saying that certain hardware platforms it's better to implement measurement-based, and I was wondering if their spam errors or measurement errors were lower.
It's nothing to do with spam errors. It's just what gate operations you can do. For example, if you have a photonic a linear optic system, you cannot do a control Z gate. You cannot do a control X gate. You cannot do these gates directly. So in that case, what you actually do is you build up these cluster states using, so it turns out you can actually build cluster states using something called as fusion measurements. You can use fusion measurements to build the RG cluster state, or you can use the fusion measurements to build the XZZX cluster state. So in their case, the only thing available to them is fusion measurements. So the only thing they can actually do is cluster states, whether it be XZZX or RG, the cost is the same. In fact, it turns out their fusion measurement more naturally implements the XZZX cluster state. RG, they have to actually do 2 extra operations. That's it. The similar thing for some bosonic qubit platforms, superconducting bosonic qubit platforms, it's very hard to do gate operations. How do you do gate operations on, your CAT codes? KerCat is different, but like it's very difficult to do gate operations. So in that case, measurements might be easy for you to do. Gate operations are harder for you to do. So in that case, again, you would want to use measurement-based quantum computing. There's another place where you would like to use measurement-based quantum computing, and I'm going to talk about that in the next slide. So yeah. Right, so with this, I'll come to the final slide, and here I'll also mention another way why this is, why measurement-based computing is useful. But before that, I would want to reiterate the message, which is, I want to reiterate the message that when you think about scaling up your system, whether it's just your, making more qubits, thinking about how you're going to make the optimize your error correction architecture, deeply think about the physical errors that are happening, and then, co-design your code according to the errors that you have. It's very important to do that. That's one way you can reach fault tolerance in the near future. As I said, the XZZX cluster state you can make in linear optics with fusion measurements. It turns out that, I did not show the circuits here, but we give it in our paper. It turns out that you can make the XZZX cluster state with only control Z gates and destructive 2-qubit XX measurements. These destructive 2-qubit XX measurements can be implemented with C0 gates, but importantly, those C0 gates don't have to be bias preserving. The XX measurements are trivially bias preserving. The only thing that can happen is your XX measurement outcome is incorrect. That's it. Because it's destructive, you're never going to use those 2 qubits ever again. So even if the C0 gate that you use converted, some Z errors to X errors or Y errors, who cares? Because you're never going to use that qubit ever again. This is not possible in circuit-based computing, because in circuit-based computing, your qubits are sitting there. You have to continue to do gates on those qubits itself. But here, you're allowed to destroy some qubits because you have the freedom to add fresh qubits into your system. So if you have, say, a fluxonium, which has bias noise, but you don't have bias preserving C0 gates in them, then, and if you want to take advantage of the bias, then you should do cluster states, not circuit-based computing. But so we are continuing to work on this, and this is continuing work by Kavya, Jehan, Harsh, and others in the group. And you should see a paper out soon on how you can what are the different scenarios in which you can use these XZZX cluster states and actually take advantage of different types of noise in the system, including bias noise, but no bias preserving C0 gates. And then we're, of course, thinking about using this for doing measurement-based quantum computing for superconducting bosonic qubits. James from Rob Sholkov's group is leading this effort. And this is really, again, because it's hard to do gates on superconducting bosonic qubits, but it's not hard to do measurements. We are also working on other things, not just the cluster states. We are thinking about how to do more efficient lattice surgery with the XZZX surface codes. There's also the XY surface codes, which have high threshold to bias noise, but there's, we don't really know how to do gates on them. They are less nice. They have some nice properties, but not so nice properties. So we're trying to see how we can actually bring them up to the XZZX surface code. We're also thinking more about how to benchmark gates so you can, get the desired information out, not just total error rate, but more about the structure of noise. Also thinking about benchmarking continuous variable qubits, not just two-level systems. Thinking about different bosonic codes, modeling open quantum systems, and so on. And if you're looking for postdoc positions and if you're interested in the work we're doing, please consider us, and we have postdoc positions open. Thank you.
Okay, let's thank Shruti virtually for a great talk. And does anyone has more questions and comments? We have about 10 minutes left.
I hope I managed to convince you that there are situations where it's better to use the cluster state approach than a measurement-based approach than circuit-based approach.
Well, I was semi-familiar with some of this, so I was sort of convinced already, but I think it's gonna, I think the measurement base is gonna be new to a lot of our people.
Right, right.
I have maybe another question or two. Firstly, you talk in this work about Pauli noise, but Pauli noise is somewhat fictitious in an actual laboratory sense, and so I'm curious how you'd have to adapt your thresholds for a general noise model, including, say, coherent errors.
So firstly, good question. Let me see how I can answer this. Yeah, so typically, okay, so the argument that is usually given is that when you have coherent errors, you can do randomized compiling. So you can, put in your poly gates in between and randomize your channel and convert a coherent channel to a poly channel. So that is a true state, absolutely a true statement. You can actually, for bias noise, in fact, you can do this in a bias preserving way. So indeed, we can twirl a bias noise channel correctly as well. So yes, indeed, we can convert coherent errors to poly noise errors without actually disturbing the structure of noise. There's also a work, I believe, I think that at least there's one work by Andrew Darmavan where they actually study the effect of coherent errors on the surface codes without doing this poly or randomized compiling or poly twirling or something. And they found a small change in the threshold, not too much. There's some sort of like twirling already going on in the surface code by itself. Yeah, the problem, the reason we choose to study poly noise is because that's the only thing we can efficiently simulate. Like, how do you simulate coherent errors? It's in the surface code. That's very hard to do. So when people study coherent errors, they usually do tensor networks. They can only study like small size codes. You can't really make statements about thresholds necessarily, or statements about logical error rate scaling for those small size codes. You have to, we really want to see what happens as you scale these systems up.
So maybe as a follow-up question then, let's say you use randomized compiling to twirl your channel. Usually this is implemented in an ensemble sense. So what guarantees does randomized compiling give you for error correction on a single shot basis? Because you're not actually twirling away your errors on a single shot basis, right? You're not doing an ensemble twirling. You're doing a randomization of a single circuit. Does that make sense?
Yeah, I'm not sure if I fully. I mean, so whenever when we calculate the logical error rate, it is including all of that. I'm not sure. So so the logical error rate includes times it failed and times it succeeded. And if the logical error rate is 10 to the minus 7, even after all these twirling things, it means that most of the time your code succeeded, even with twirling, otherwise not. So I'm not.
So I guess my point here is that you cannot actually twirl into a stochastic Pauli channel unless you do it in an ensemble sense, right? So, and that means many shots, but you're interested in actually performing error correction every time you take a shot or implement a circuit, right?
Yeah, well, I was trying to say, like, if you're running, let's say you're running an algorithm, or you wanna, then you want to run it once, not a bunch of time, in order to do randomized compiling and get the advantage of randomized compiling.
Well, if you don't believe in randomized compiling, then
We do believe in it. We worked on it a lot, but you need to do it many times.
I guess my point is that unless you do it in an ensemble sense, you're not actually getting rid of all your coherent errors. So I'm like, it's just, yeah, I'm personally, I'm actually curious in this topic. How do you ensure you actually only have Pauli noise on a single shot basis so you can efficiently perform
like
correction?
one thing I can say is we did simulations where we actually, for small system sizes up to 9x9 codes, we simulated a polynoise approximation and an exact coherent noise channel. So we actually applied the exact inversion operation to this thing, and they both perform exactly the same way. So whether we twirled it or did not twirl it, it actually didn't make much difference. And one way to think about it is the error correction code itself has some sort of twirling in it, in the sense that, so suppose the error that was happening was like identity plus some small z, right? It's a coherent error. It's literally identity. You know, it's like e to the I theta z error happening on your system. Now, when you do measurements, you are either going to project measurements onto the identity operation, or you're going to project the measurements onto your the z operation. So that kind of is already removing some of the coherences in your circuit.
That's certainly true. That's the main purpose of quantum error correction. You're digitizing your non-digital errors.
Yeah, and yeah, I mean, it doesn't make again, as long as your coherent errors are not too large, it's like I really don't think we will need randomized compiling anyways. Yeah. And that's because we have simulated it, and at least for small systems, it doesn't show any difference.
No, this last thing I understand. Like when you're doing error correction, when you measure your ancilla, your collapse rate function, and then you digitize the error.
Right.
Although, I'd say errors like this are not trivially along the same axis that you're measuring.
Yeah, no,
So
yeah.
like
If it's misalignment errors and stuff like that, there might be issues. But
I didn't get that comment.
Well, you gave the example of a z error and then measuring along the z-axis, but you can have errors along x-y combination.
Yeah, but you're measuring, but exactly, you have two stabilizer measurements going on. You have the x stabilizer measurements going on, and you have the z stabilizer measurements going on. So you're automatically collapsing all x, y, z, all x, y, z.
Yeah,
this is true for everything.
I'm saying they don't have to act along any of those directions. You can act along any arbitrary direction, right?
But that's what I'm saying, right? Like, say your error is identity plus pz plus px. I can write any error as linear combination of I, z, x, y, right? And so the syndrome corresponding to a z error is different than the syndrome corresponding to an x error is different than identity, different than y. So basically, the moment you do any measurement, you're going to project yourself mostly onto this one of these four possibilities. So it doesn't matter if its rotation is along some other axis.
Yeah, and that's the key point, Akel. Once you do your ancilla measurement, you collapse into one of them, even if you have some linear, even if you have some superposition. In fact, that's why this type of error correction was invented. Just to beat the fact that if you have something that was analog, like our devices are, then you will never get low enough error rates without digitizing it. And so error correction sort of does that for you.
Thanks.
Okay, and I think with that, we've reached our time. Let's thank Shruti again. That was a very good talk and very clear, Shruti. Thank you.
Awesome. Thank you. Thank you for your questions. This is super awesome.